You all have probably already seen one of these devices before. This is just a hand crank flashlight. It's got a series of LEDs along the front, and inside of this it's got a capacitor to store the charge, and this generator basically charges up the capacitor. I want you to look at the light and to think about these graphs that we're going to see. We're going to see the brightness, slowly start to climb and get higher and higher and higher. And then once I quit charging the capacitor, you'll notice that there's this exponential decay in brightness. So it's really an exponential rise in brightness and an exponential decay in brightness that we can predict mathematically. The two things that video demonstrated is the charging and discharging of a capacitor. The charging circuit for a capacitor in its simplest form is just a battery with a switch, a capacitor, and a resistor. So you close the switch and you start to get a buildup of charge, of positive charges on this plate, negative charges on that plate. So there's 4 components in the circuit for charging a capacitor: battery, switch, capacitor, resistor. For discharging a capacitor, you just take out the battery, and before closing the switch, you have a capacitor that is fully charged, or partially charged, and so you have a capacitance C, resistance R, like that. And so what will happen is that this circuit will try to neutralize the capacitor so that there's no net charge on either side. For those of you that were in my engineering 111 and 112 classes, you might remember the charging circuit that we encountered on the camera, disposable camera flashes. So if you're trying to think about how these two diagrams, these circuit diagrams, relate to this device, there's a button on here on the front which basically starts to charge up the capacitor that was inside of there. And so here is the button. There's our AAA or AA battery. Remember the big cylindrical black capacitors that were in there, and the circuit had some residual resistance, or maybe some resistors added in there on purpose as well. So that's what that button right there does. That's the charging circuit. And of course, on top of this, there's a button here which basically is the flash. It's the other switch. It's down here for discharging a capacitor. So there's that button. It's the same capacitor, but the resistor is now something different. It's actually the bulb. Now the equations that describe the voltage drop across those capacitors, whether they be inside of a flashlight, rechargeable flashlight, or inside of a flash camera, the equations look like this. The voltage drop across a capacitor is going to be time dependent. So this is where we're starting to get into AC circuits, because now the voltage depends upon time. And so what you have is that at time equals 0, this term over here is essentially gone. And so, wait a minute, that's not right. At time equals 0, this term is 1. So then you basically get a voltage drop of 0. And you should expect that, because you might remember that the voltage drop across the capacitor is equal to its charge divided by its capacitance, Q over C. And so initially there's no charge on it, so there's no voltage drop across it. So that agrees with that. Now if you wanted to plot this, maybe I should bring this in for the plot. Then what that means is that at time equals 0, the voltage drop across the capacitor during charging starts at 0, and it's going to asymptotically approach the voltage of the source. That's what the S stands for. That's the voltage of this source. That was the AA battery inside the camera flash unit, for example. And so by asymptotically approach, I mean this is our reference line, and it's just going to be kind of an upside down exponential, like that. And you can see why it's upside down. It's basically a constant minus an exponential. So we just say that this is asymptotically approaching Vs, and theoretically it gets closer and closer to Vs, but you never really can fully charge a capacitor, because it takes an infinite amount of time to do it. And the rate at which it charges up depends upon your choice of resistors and capacitors. So that determines how fast it charges up. You might remember that when you press this charge button right here, that it takes a while for that red light to come on. And that red light is supposed to say, well, the capacitor is charged up. Well, it's not saying that it's completely charged. It might indicate that that it's 90% charged or 95% charged. So that's what that light indicates. Now, when you're discharging a capacitor, remember that you remove the battery from that. You have the same capacitor, and then you have the bulb here, for example. It could be a resistor also. And the equation now looks like, well, just an exponential decay. Now we got to change the subscript on this from Vs to Vi, because this is the initial voltage that was across the capacitor. And then you have an exponential decay over time. So at time equals 0, you just start off with the voltage drop across the capacitor being Vi, and then there is well, an exponential decay. That's the equation for an exponential decay. So it asymptotically approaches 0. This also means that you can never really completely discharge a capacitor either. It takes an infinite amount of time to do that. And the length of time that it takes to discharge a capacitor depends upon, again, your choice of resistors and capacitors. You might remember that in Engineering 111 and 112, if y'all had that from me, that we took a screwdriver and we put it across the terminals of the capacitor that was in this device. And because the resistance of the screwdriver was really low, that makes this time constant, that's what this is called, by the way, RC time constant, really short. So with that being said, here are a few short notes you can add to homework 4 to get you going. On problem 1, the equation to use here is 4.9, found in chapter 4. That's what this is all about here. And the drawing that you can make for problem 2 is the circuit in which you have a capacitor that is discharging. So there's the equation, the initial voltage, and our time constant is over here. So that's what all these things are here. And all you really need to do is say that you're looking for I think one of these variables. I can't remember which one it is, but basically what you're trying to do is you're trying to say that at 60 seconds you have 90% of the initial voltage. Now the reason I'm doing quite a bit of this for you is because we really haven't had a chance to meet and discuss this in class, so I am doing quite a bit of this for you. And the only way this can be 90% on this side is, according to the statement of the problem, is that if it was 60 seconds. I'll have to let you fill in what the R and the C are. In fact, I think one of those is an unknown. So one of these values and the other one is the unknown that you're solving for. Just going to put it over here. The VI's cancel out. So you have to take the natural log of both sides to get the answer. I'm going to let you do the rest of that. On problem 3, this is an equation in which you are charging a capacitor. I think I've misplaced it. This thing over here is tau, and tau is just the denominator of this exponent. Basically it's RC. And you calculate that, and you know that the voltage of your source is 100 volts, so you know that it's going to exponentially rise. But I want you to actually enter numbers into your calculator. For this, let's have it, I guess 1, 2, 3, 4, 5 data points along here. And I can tell you the first one's going to be right there, because you put a 0 in for time, and I could see that I made a mistake. So you put a 0 in for time, and these two terms cancel out. That becomes a 1, so it's 1 times Vs. Vs minus Vs gives you 0. This is going to rise, but I want you to actually do the calculation and make good estimations about where these data points are going to be. Alright, problem number 4. This is an exponential decay, so this is a discharging of the capacitor. And I don't know if there's anything else I need to give you on that. They give you some of these parameters. Oh yeah, I think you're looking for the resistance of this. So yeah, so basically it's very similar to problem number 2 above. On problem 5, this is an exponential decay type of problem, and discharging of a capacitor again, but you're going to be looking for the time. So now it's asking you to figure out how long does it take for the voltage to drop from some initial value to some final value. So that's what you're looking for.